Thanks, Olivier. So discussing with Olivier, I actually realized that I might have to give you a lot of background about what I'm trying to talk about today. It will be some modeling, but a different type of modeling of surface processes. And I will show you, in addition to this, or as part of this, the most recent development that I've actually accomplished in that field. That is the modeling of the evolution of the Earth's surface, the shape of the Earth's surface through geological time. What I want to talk also about today is dynamic topography, which I think has become, or has received a lot of interest from the scientific community, the Earth sciences community, for all sorts of reasons, good and bad. And because I want to work, and I've worked in geomorphology, I actually realized that there's a big potential to actually kind of combine the two and see how we can in fact erode, whether it's important, what we can learn from that dynamic topography. And maybe what I've tried to tell you, and I'm not exactly sure what you guys are. I think you're physicists, geophysicists, earth scientists. So I'll try to be very broad in describing what I want to do today. But what I really want to point out, I think, is that this is a great opportunity, the study of dynamic topography, to have geomorphologists and geologists in general provide constraint on something they usually don't think they can really contribute to, something like mantle dynamics, which usually is reserved to the geophysicist or the physicist. So, I gave a talk a little bit similar last week in Oxford, and I realized that after giving my talk that nobody knew what dynamic topography is, so I felt really stupid because I forgot to tell them. So I'm going to spend some time explaining what I mean by dynamic topography. You might know, you might not. I'll do it. I think it's important. So, surface topography at the surface of the Earth is typically, as we understand it, the result of thickening or thinning of the crust, mostly of the lithosphere. When you thin the crust, you subside the surface by isostasy. And you can include some flexural component to this, but it's basically variation in crustal thickness, or let's say in plate thickness, lithospheric thickness, that determines whether we have a mountain or a basin. Yeah, and then surface processes act on that to erode the mountain and fill the basin. There is, however, another source of topography at the Earth's surface, or any planet. It's to do with the motion inside the mantle, the fluid-like motion inside the mantle, that causes, due to the fact that the surface is fixed, it causes either through the divergence of that flow of things that are going up, or the convergence of things that the flow around things that go down, it produces a stress, a viscous stress at the base of the lithosphere, let's say. And the only way, because we have to have static equilibrium of forces, the only way the system can compensate that stress is by creating topography. Okay? So that is not isostatically compensated. So if you want a broad definition of dynamic topography, it's the topography that is not isostatically compensated. It comes from fluid-like motion in the Earth's mantle. It's not new. This is I think one of the early paper, 85, by Brad Hager and colleagues, that kind of define dynamic topography. And I make the point that there must be of the order of topography of the order of a kilometer high, both at the surface of the Earth and at the core mantle boundary. Both surfaces are deflected by the viscous motion in the mantle, by the convection in the mantle. And from what they knew from the structure of the mantle, they actually show these early figures of what topography, that dynamic topography should look like. And they also make the very important point, it must exist. It's the only way we can actually explain the shape of the geoid at the surface of the Earth. If you don't take into account that the variation in the shape of the surface due to mantle flow, you get basically the wrong sign of the geoid. So it's important, but it's not easy to actually quantify it and decipher it from the normal topography. We have mountains and basins related to motions of plate at the surface. How do you figure out what is dynamic topography and what is not dynamic topography? Well, we can subtract what we think is real or isostatically compensated dynamic topography by saying, well, I know the thickness of the crust everywhere on Earth, I know the thickness of the lithosphere, I can predict the topography, I subtract them from what we know, we measure the topography quite well, and that gives us something like this, okay? Of the order of a few kilometers in amplitude. And you can see that it varies in places. There are places where it kind of makes sense. The uplift of the East African Rift, subsidence under the Andes or the Amazon basin, or eastern North America. These are more likely related to subduction, which induce a flow which sucks down the continent, and this is clearly upwellings that produces a positive stress, if you want, at the base of the lithosphere. There's another way you can do that, is much more sophisticated if you want, more appealing to physicists, is you can actually, and I'm not going to go in the details of that, but it's a fairly detailed procedure you have to go through, but you can use seismic data, tomographic data, to infer a seismic velocity structure for the Earth, for the mantle. And then you say, I know that most of these variations are related to temperature, maybe composition, and you make a relatively well-educated guess at that, and you can derive from that a density structure for the mantle. And then you have your driving force. You only have to add a model for the viscosity of the mantle, and then you can make it move, and you can predict the flow in the mantle, today's mantle, and you can predict dynamic topography. And this is this is now in a spectrum of that topography, and you can see the black line here is the spectrum of the dynamic topography. You compute that way, and you can see it has wavelength, amplitude of a few hundred meters here. Spectrum tends to smoothen the topography. So it is typically, if you look at the map of this, would be also an amplitude of about 1,000 meters, and has wavelength kind of starting around 1,000, but more at the planetary scale is where most of the amplitude of that topography is. Note also that it is a very, for us looking at it from the surface, it's not something that moves very much. And why? Well, because the mantle changes in mantle dynamics are very, very small. Mantle dynamics is small, but the changes in mantle dynamics is even smaller, slower. And so if you look at, this uplift rate predicted by this model is very, very small. It's not tectonic. It's almost 3 orders of magnitude smaller than the change in surface topography height associated with tectonic motion. So, I go here through the procedure from the seismic, the tomographic data, how you have to add. I thought I had moved that away from in my presentation. So, but this is simply what you have to assume together. How with depth the relationship between density and seismic velocity goes, and you see there are uncertainties on that, a lot of uncertainties. This is what we think we know about the radial viscosity structure in the mantle. Again, a lot of uncertainties. And this is just the radial component. If we want to take into account lateral variation associated, for instance, with subduction zone, which are colder and therefore stiffer, it makes things even harder. And this is an example. This is what I wanted to show you. This is a prediction from one group. There's several groups working on this in the world. And this is a prediction of the dynamic topography beneath Africa. And it kind of makes sense. You'll see the East African Rift. You can see the Ogard. You can see uplift maybe of the Cap-Val Craton. And subsidence in the Congo Basin, although geologists would say that today there isn't much happening in the Congo Basin. And subsidence and tilt of the Arabian Peninsula, which is well documented. So there are things that we can predict using these methods that kind of make sense. But geophysicists never stop there. That would be too easy. They also say, well, can we predict that dynamic topography in the past? That's 30 million years ago. And how do they do that? There are about 2 big methods to do it. They have to make the mantle convection model more backwards in time. So we all know that viscous creep flow, very small, highly viscous flow, is perfectly reversible. So that's fine, we can do that. But we also know that convection is driven by thermal anomalies mostly, and that we can't do. We can't run thermal diffusion back in time. That's a no, okay? But they do it. Okay, that's one group here, Forte and Mucha. They just do it. Just change the sign of delta T in the convection calculation, and then produce a mantle flow and a prediction of dynamic topography 30, 40 million years in the past. You can go much further than that, because you've got all the problem with the thermal boundary layers that you can invert very well, and it all breaks down. There's another method called, it uses what are called adjunct methods, which is more or less the same, except that in addition to that, you impose some kind of a smoothness condition on your inversion as you go back in time. I won't go into detail of that, but you can do that, and it's really interesting, just doing that, you can show that the evolution of the East African Rift systems took place approximately over the last 30 million years. And if you look in the geological record, that works quite well. And I'm really surprised when I see that, when I see all the assumptions we had to do to get there. It's really, in my view, quite remarkable that it works that well. I won't go through that. That's another example I'll come back to. There's another group, and see, they're trying to predict the dynamic topography associated with subduction beneath North America. And this is what today the tomography looks like, and they assume what we want to see how it has evolved through time. So that's the dynamic topography compared to today, if you want. And just one point here, they predict that over that period, the whole of the continent has been tilting at some rate, and that also, I'll show you some data, is well constrained by the geological record. However, they had to do all sorts of fancy things in the viscosity structure of the mantle to actually get these things that we know are subducting plates. So this is tomography data. So we see the cold stuff in the mantle today. They have to do all sorts of things to get them to behave like subducting plates and not like blobs that simply go up and down. Okay? So it's not an easy calculation to do. There are lots of assumptions, and yet you get to something that kind of makes sense. But it doesn't always make sense. And there are many groups doing that, but there are two big groups competing, very highly competing. It must be some of you here must be aware of that. That's the Canadian group, if you want, with Forte and Mucha. And that's the Californian group with Mike Gurnis. And this is an example of what happens under the Colorado Plateau. For those of you who know it's roughly the Colorado Plateau on the western side of North America. This is the west coast of North America here, and this is the Colorado Plateau. Okay? And really interestingly, by making this going backward in time, we all see today something that's pushing under the Colorado Plateau, and is responsible very likely for this anomalous topography. Well, this is the variation in topography computed by the model, or the accumulated dynamic topography. And you can see that in both cases, nothing happened for that group in the last 40 million years. The blob has been there for 40 million years, and it got there before that. And in this group, when they make the mantle convection go backward, they show that all of the topography is created in the last 30 million years, almost linearly. So clearly, is it the viscosity structure they use, the conversions from seismic wave velocity to density, the numerical method they use to invert mantle flow? Clearly, we don't have the answer to everything. These remains very speculative models. And so the point that I'm going to develop here is that this is where geologists come in. And, I think this is a great opportunity we have to talk to the geologic community and get their information, the information they have about that. I'll give you a very quick example or two. The tilting of the North American continent. This actually was already published in '89. There's this very long wavelength sedimentary wedge that crosses most of North America from east to west towards what was the Laramide orogeny. And clearly, the only way you can explain that is way too long to be a flexural effect. It cannot be a load that deflects the plate. That would be only about that wavelength. The only way is you need to tilt the continent. And it was shown back then already, the most likely force for that is subduction. When you have a subduction like this, you induce a flow here, a corner flow, and that flow, just by being there, creates a pressure difference beneath the plate, which increases. In fact, if you solve this analytically, there is actually a pressure singularity there, and you can show that you must tilt the plate. And the amount of tilting is a function of the dip, the velocity of the subduction, etc., etc. And because it's such a long wavelength sedimentary wedge, even after you rebound it, when the subduction ceases, you will preserve most of it. It will take a very long time to erode this very, very, very long wavelength sedimentary basin. That's evidence. Another one, I like this picture. You can get it from Mike Sandiford's website in Australia. This is a highly exaggerated geoid. Okay, so you can see where you are with respect to the geoid. And he made the point that over the last 15 or 20 million years or so, and this is great when in Australia making that, Australia is actually been surfing a geoid high. Okay, so in fact, if you look, and the reason he came up with that is because there's a very simple geomorphic observation in Australia, is that the south is characterized by big terraces. I don't know if you've ever been there, okay, but clearly this coast is emerging and has been doing so for the last 5 or 10 million years at least. Whereas if you go to the north, it's swamp. It's a subsiding coast. Okay, so the relative coastline, or the coastline was, the old coastline is somewhere offshore now in the north, and the old coastline is somewhere onshore today. And you can date these shorelines and show that the tilting has about 5 to 10 million years in age. So again, this, most people, can only be explained by dynamic topography. Topography over which a continent moves. And I will come back to that. It's very important. Okay. So, now I'm back to, let's put my head as a, well, I'm not really a geomorphologist, but I work in a bit in geomorphology, modeling geomorphology, geological processes. So let's take the point of view of the geomorphologist who studies the Earth topography and how it's created and how it evolves through time. So he looks at dynamic topography. Well, he's going to say, well, we're not kind of used to that kind of topography. And the geomorphologist looks at, an uplifted shoreline and a mountain belt, at a scarp, something that has a dimension of a tectonic, at most, a tectonic event. So this is very unusual for a geomorphologist. It's very long wavelength, minimum 1,000 kilometers, and it's very low amplitude, less than 1,000 meters. And for a geomorphologist, when you go in the field of a geomorphologist, first thing they look for is slope, because everything happens where there is slope. And these are very, very, very small slope, so they won't see it, and they'll say, well, it's not really important for us, that kind of thing. It's extremely slowly varying. Once you've established the flow in the mantle, it will take hundreds of millions of years for a plume to go up, or a subduction to go all the way to the bottom of the mantle, and the dynamic topography it creates will basically not vary, or vary very, very slowly. Unless, and this is really where things start maybe to get very exciting, is that if you have a fixed source of mantle dynamic topography over which you move a plate. You can see that if you have something that's pushing up the continent and you move the plate at 10 centimeters per year, then locally you can have uplift rates of the order of 10 centimeters per year. Simple by horizontal advection becomes vertical motion. So you can get in a situation where you produce topography at a rate that's similar to tectonic topography, to isostatically compensated topography, due to the motion of the continent over the mantle. I'll come back also to that. So, I put that up because I kind of guessed that you don't know much about what a geomorphologist does and what are the tools he has to constrain the topography, but mostly to constrain how it's created and how it's evolving through time. So, a geomorphologist measures topography, and I can show you, this is really exciting. We can also measure with great detail past topography. This is a paper that came out in Nature Geoscience recently, late last year, by Nicky White's group in Cambridge. And they have very high resolution 3D seismic. And by following a horizon, I'm not in that field, I'm sure many of you are much better, they were actually able, simply digitizing it very carefully, to reproduce an ancient topographic surface. And from that, they inferred that that basin was subsiding along a margin somewhere, and then there was an event that brought it through the surface. It was exposed to aerial erosion, and then subsided again and was sedimented again. And I can see it. This is not a topography, measured on land. This is the geometry of the seismic reflector. And I even went further, and I do what geomorphologists do. You can actually look at the profile of these paleo rivers, and from that, over there, I'm not fully agree with this. If I had read the paper, I don't think we would have gone through. But you can tell from the profile there how long it takes for a river, what we call a nick point, so a disturbance in the river, to propagate up the network. And by doing that, you can also estimate how long that system, that surface, was exposed. So the duration of a sedimentary hiatus, basically. It's really exciting stuff. You see, you can measure topography, but today, and potentially also in the past, in some circumstances. The thing that geomorphologists have real trouble doing is measure what we call paleoaltimetry. That's to say, how tall was a mountain or a plateau or any place of the Earth 10 million years ago. The absolute height of the surface of the Earth with respect to the center of the Earth, we have almost no tool to say something about it. Okay? It's very hard, for instance, to say if the altiplano was at 5,000 meters or 2,000 meters, 30 million years ago. We have methods, you know, we can use all sorts of methods to do it, but the error bars are as big as the measurement, basically. I'm exaggerating, but we're not very far from that. There are other things we can do, which are much more precise, but they all are relative tools. And most of them, we use, for instance, thermochronology, low temperature thermochronology. We can measure the time a rock cools through a given temperature with very high accuracy. So if you assume that the rock is being exhumed due to erosion and the formation of a landscape, that we can date very well. We can tell how much has been eroded, when, and at what velocity. We can also use the sedimentary record to do that. We just sit next to the surface and see what happens, how much sediment comes, where it comes from. We have other tools to say which part of the landscape is being eroding at that time. But all of these methods, as I said, are relative, and all of them, I'll come back to that. All of them depend on the topography being eroded. If you just inflate the topography and then bring it back, like dynamic topography typically do, if you don't erode it, it's going to be extremely difficult in the geological record to actually see these events. We can see some, but most of the information we'll have is when this system is eroded away. I won't go back to the slide I showed you. It shows how we can use thermochronology to say something about the exhumation of rocks and the burial in sedimentary basins and time that. Okay, so we have a tool to say when a rock was brought to the surface and buried in a basin, both periods of time, we can track them quite well. But it only happens if we erode the surface. If we don't, we have no mean of actually quantifying the amplitude or the timing of the uplift. So, if we want to erode it, if we need to erode it, the question is, are these long wavelength dynamic topography signals, are they, the right length scale or height scale or length in duration, whatever, to produce sufficient erosion so that we can actually document that? So, are surface processes, erosion by all sorts of means, efficient enough to erode dynamic topography? Okay. Just to give you an idea of how much we need. If we want to use this method of thermochronology, we need at least rocks to come up from about 2 kilometers to cool through the top 2 kilometers of the earth to record anything. So we need erosion, incision of about 2 kilometers. What can we hope that dynamic topography be eroded that much when it happens in the past? There's a really good thing about dynamic topography because the driving force is constant. In other words, if you have a plume or something pushing or pulling down the surface, if I erode the dynamic topography, the mantle needs the weight of the topography to compensate its driving stress. And the driving stress of the mantle never stops. So if you erode topography, the system has to adjust to recreate the topography. It's the perfect phoenix. You remove the topography by erosion, it comes back up. And the time scale for recreating the topography you can show is determined by the viscosity of the asthenosphere. So it's basically glacial time scales. Glacial is just tens of thousands of years, not tens of millions of years. So for a geomorphologist, that's great. I erode the stuff, it comes back. So in theory, I can erode a lot. Okay? So even if I erode a little, it doesn't change. I keep eroding it. There's a limit, of course. You want to erode all the way to the core mantle boundary, even if it's very efficient. Because as you erode the surface, you also bring the mole up, the crust mantle density interface. And at some point, even though the density between crust and mantle is smaller than between crust and air, okay, you will create dynamic topography on the mole, which after some point will compensate the driving stress from the mantle. You see what I mean? You can show, in fact, that if you create 1 kilometer of dynamic topography and you erode it, you can do exactly the same thing by creating roughly 7 kilometers of topography of the mole. That's the ratio of densities, it's about 6 or 7. So if I have 1 kilometer of dynamic topography and I have a very efficient shovel or bulldozer at the top, I can exhume about 7 kilometers of rock. See, that's enormous, It's a really large amount. So potentially, the potential is there to erode a lot. So, what's the driving parameters? What are the main important parameters to determine erosion rate at the Earth's surface? Well, we know it has got to rain, it's got to have ice on it. So climate is kind of important, but in general, there are two things that matters. One is slope, rate of erosion, or the stress imposed on the surface and needed to erode stuff is proportional to slope. Gravity does everything. And surface area. Why? Because the more surface area drains in a point, the more discharge, the more water will flow there in a river or along the hillside, and the more efficient the system will be to erode. Okay? So, no, large dynamic topography creates small slopes, so that's not good. But dynamic topography creates very large areas that are affected by that and will drain water in a single direction, if you want, and that potentially will be good. And so we have two competing effects here. I won't talk about that, it's another whole lecture. So, I'm not worried about that, but I want you to forget this data as soon as I've shown it because it's unpublished yet and it's not my data, but I think it's blurred enough in here that you will not remember it. Why do I show you that? Frankly, until about a month ago, I was giving talks like this and saying the slopes at the surface of the Earth are way too small when created by dynamic topography, and you can't erode it. It would take millions, hundreds of millions of years of erode dynamic topography. And this colleague of mine, Xavier Robert, he was on a postdoc in the US, and they collected low temperature thermochronological data on top of the Colorado Plateau. You know, if you've been there, this is the Grand Canyon here. You know, it's a total flat area, except for the Grand Canyon. And I'd say this is a very old, no, nothing happened there. These are the ages. There are points missing in there, but there's a whole bunch of points here. Okay, and the trend goes like this. Okay, and what you see, that point here tells us that in the last 4 million years, you have very recently for a geologist, you have eroded about 2 kilometers of rocks there. So like in the geological most recent past, we have removed 2 kilometers of rocks here. And if you follow that trend, those 2 kilometers minimum, it could be much more, we don't know, were eroded as you go along this line, roughly the last 10, 20, 30, 40 or so million years. So basically there's a progression in age here that shows that there's been, no, it's not an uplift, it's an erosional wave from there to there of at least 2 kilometers. So when I saw that, I say, if this place is sitting up like it is now in the Colorado Plateau because of dynamic topography, bingo, of course. It's clearly shown here, you do erode dynamic topography. And then in addition to that, if we believe one of the two models I showed you earlier for this area, this is exactly the timing that they predict that the dynamic topography should have gone there. So it's perfect match. So then you really go, whoa, what did I miss? Okay. So first part finished. I have to go a bit faster now to show you why I think it works. Okay. Why you do erode dynamic topography. And it's really exciting. There's a lot of information there. So how do you erode at the surface of the Earth? Well, beautiful picture. This is taken in north of Montreal in Quebec. And this is a classic in a river with lots of big rounded or not so rounded big rocks in it. These are the guys who do most of the erosion. These big, what we call tools at the bottom of rivers. And even though they look pretty stable there, most of the work in a river is done at times of big floods. You know, the centennial or the millennial flood, where these things can move down this river by, over kilometers of distance of kilometers. And I'm making a very condensed lesson in geomorphology. All geomorphologists will tell you that in most areas, not everywhere, it's the rivers that do the work. The rivers inside the bedrock, carves it, creates slopes on the side of the river, creates the gravitational instability, and the hills collapse into it, and the river takes that and flushes it away. And the stuff that comes in becomes also tools that will be used to further erode the river. So the point that geomorphologists do, if you can predict the incision rate of a river, you've got it all. The rest will follow. Okay? And of course, there we go. I'm a physicist, so we need equations to do all this. They are relatively simple equations. And I must tell you, they have become much more complicated because now we start to look in the detail of how this works. But as I told you, the river network does all the work and the hill slope follow. Very simplified. This is the basic equation for the evolution of the height at the bottom of a channel, of a river. This is uplift due to dynamic topography. Okay, so or uplift due to tectonic motion, whatever. It could be subsidence if it's negative. And this is the erosion of the river, the constant. And there are two parameters that matter: the local slope, dz dx, if you want, and the drainage area or the discharge. How much of the landscape drains? So when a drop of water falls on that landscape, how much drains in that location? Two parameters, two some powers, m and n. M and n are between 0.5 and 1.5. Right? They're not 27 and 0.01. It's not linear, but it's almost linear. And what we do with this, obviously, I'm going to show you now, and I'll have another 5 minutes at the end to show you how I do it in detail. We can actually solve this equation. We may have to add a term here. That's the horizontal motion of the plate on top of a static plume. So static source of dynamic topography. So that's an advection with respect to the source of uplift. So this is again v dz dx, and dz dx is the slope. So you see the slope appears here as well. And if you want, you can also add a term, which I won't talk about here. This is another talk I have, which has to do with the deposition, because also rivers carry and deposit the material they erode. But I won't talk about that. What we do with this, we solve them, and I'll show you, this is a terrible way to do it, but this is an example of how we solve them in plan form. So we can produce beautiful landscapes numerically. And I'll show you how I do that. This is an example of a simple landscape that I've taken, and I'm tilting it from left to right all the time like this, simulating the passage of a wave of dynamic topography. There's no sense. As a physicist, it doesn't exist, but I'd like to study the system by doing that. And what you can say, what I want you to show, is that the rivers that you create, or the valleys, the topography, is very stable. It's just the amplitude that seems to vary. Once you've installed a river somewhere, it's carved into in the landscape, and it's very stable, except near the divide. Okay, here we have two sides, one flowing that way and one flowing that way, roughly. And the division between the two, we call it a water divide. That is extremely sensitive to even a small tilt. Okay, so if you take a landscape with rivers flowing and you push it on one side with dynamic topography, you're very likely to change the geometry of the divide of where the water is flowing. But the details of the landscape, that's going to be very hard to change away from the divide. I'll show you how we've done this if I have the time. For those of you, I guess there may be a lot of here who are modelers, and see how we do that. It's actually a fascinating work. So I'll remind you that while we have this problem, can we actually do something with these equations and prove that yes, dynamic topography can be eroded, and at what rate, and how important it is. So what I've done here is an experiment in one of these landscape evolution models, as we call them. So we predict the evolution of rivers, how they erode and transport, etc. It's a very sophisticated model that I wrote about 10 years ago, and quite inefficient. But for this, it doesn't matter. I'll show you some results. And in the last part of the talk, in the last 5 minutes, I'll show you what really excites me these days is do a new version of this using new algorithm and new computer technology to actually do quite amazing things in this field. And I hope to develop that in the coming years. So what I've done here is not just draw a line. This represents the lithosphere. Okay? And I'm going to apply a flow, which I don't compute, apply, which is going to create a stress that's got a kind of a Gaussian shaped stress at the base of the lithosphere. And I'm going to assume that the lithosphere is elastic and has an isostatic compensation to this. Okay, so it will create some topography. I'm going to erode that topography by raining on it, okay, numerically. And then, like in the Colorado Plateau, although in the Colorado Plateau it's likely that it's the mantle that's moving, or the plate that's moving, or not, it doesn't matter, depends on which system of reference you use, but here I'm going to move the plate at a set velocity and see what happens. So I've got a series of little animation to do that. This is a plan view, so you're looking from top, and this is a cross-section in the middle of the model here. Okay, this is about 1,000 kilometers long and only, 50 kilometers wide. It doesn't really matter what happens in that direction, as long as you have enough degrees of freedom to have rivers that flow and can change the geometry. And this is topography. I'm going to play it once and you'll see what happens. So we're going to spot the topography, and then the topography, the uplift is going to migrate, or the plate is going to move. Okay, the black line is the predicted topography along the middle here. Okay. The yellow line here is where basement is. So if basement is here. Okay, it means that basically, it's not basement, sorry. It's the position of the original topography. So this is the amount of erosion and sedimentation. These are sediments that have been deposited. This is the amount of erosion we predict. These are sediments. And the colored lines here corresponds to different, what we call stratigraphic horizon in the sedimentary basin that has been created. So I'll play it again. Okay? And so what we want to look at is, of course, the topography. This is the amount of erosion here. Okay? This is the line that was at 0 at the beginning. So that's the amount of erosion here. And that's the amount of erosion and sedimentation. And what you see is very interesting. If I, sorry, it's the wrong one. I want to go back to this one, yeah? As you create the topography, there's a first stage, but the topography is ahead of the forcing function. And then the second stage, where it kind of moved back, but it's still ahead, okay? And the difference between the two modes is that there is also sedimentation in the front or not, okay? I won't go too much of why we have these two modes of propagation of the wave, the surfing topography. The reason that the topography is not aligned with where I push, okay, is because it's moving. And when you move something and by pushing it, ahead of it, you're uplifting. Behind it, you are actually going down. Okay, so the resulting topography that you're eroding, it's normal, it's actually centered where there's a maximum uplift rate, not the maximum uplift. And that's why you explain. And you note that we can easily produce about 1,500 kilometers of erosion of that system. It depends on the model parameters, which we don't really control, but you can do it with reasonable values for these parameters. And also it predicts there's a long trail of sedimentation in the back, which records the evolution of the topography and its erosion. Let me just do quickly one thing. I could play with many models and parameters. I'll change the velocity at which it moves. The solution is almost identical. If I do that, get the same behavior, it goes faster. I first have this first stage and then second stage. The main difference is that the topography is now, although it's not exactly the same scale, you can show this is a side effect here. The wave is coming out of the model, so I'll play it again. The topography is about 25% higher. I'll play it again. Okay? And there is less erosion. You don't leave enough time for the erosion to act. But it's interesting that now I predict that if I'm on the field measuring the dynamic topography, the higher the topography, the less I will erode it. It's already kind of counterintuitive. And this is the last, by moving it more slowly or slowlier. Okay, you get slightly less topography, but because you go slowly, erosion processes can act much more efficiently, and you produce much more erosion. And you can produce 2 or 3 times, even more, erosion than you actually have topography. So, I'm with physicists, so I allowed myself this morning, I actually put equations in my talk, which I never do, because when I talk to geologists, if I have a single equation, I fall asleep. It's very simple mathematics, though, is can we estimate roughly, when a wave like this goes through, how much we're going to erode? That's the key question. And it's actually very simple to do. If you assume that the topography doesn't really change, the dynamic topography is always recreated by the stress in the mantle. If you assume that the erosion law, erosion rate is K, slope to some power, drainage area to another power. If you assume what we call Hack's law, it says that if the drainage area is basically a nonlinear function, but a function of at the point here, how much you drain is simply a function of the distance to the divide. This is the distance to the divide to some power. Right? You put that in there, get that. If you take that, put that in there, it's a simple derivative of a Gaussian shape. You get that. And then what you say, this is the local erosion rate at any time, at any place. I'm going to integrate it at a given point at x equals 0 over minus to plus infinity in time. So that gives me the total erosion, the total maximum erosion. You get this equation, the integral. You can see it's symmetrical, so you can easily solve it, and you end up with this, where this is a constant, which we could find a solution, but I'm not interested. And what we get is this formula, that the total exhumation is proportional to the initial height, the height of the dynamic topography to some power, times the width of the system to another power divided by the velocity of propagation of the plate or of the wave. That makes sense. The higher the velocity, the less I will erode. I've seen that in my experiments. But what are these exponents? Well, we don't know really what they are. But there's something really amazing. H is well known. You can easily measure it. Okay? You can go in any landscape and measure the relationship between drainage area and distance to the divide. And it's very stable. It varies between 1.8 and 2.2. M and N are very hard to measure. But you can actually, from the profile of a river, it's very well known, you can constrain the ratio between the two. And that's almost very close. Everywhere on the planet is almost equals to 2. It's called the concavity index. It's about 2. If you take that and put it in there, you can actually show that this cancels out. For all value of Mn that satisfy that. And so you end up with this. And that's really fascinating that the total erosion, and I told you erosion is proportional to slope. If it was proportional to slope, it would be that divided by that. That's the height, that's the width. And you show here that because there is also that depends on drainage area, that dependence wins. And therefore the lambda appears on top here. And so the wider the topography, the more you will erode it. And it's not the slope that wins. So that, in my view, explains nicely why you would expect dynamic topography to actually be eroded, even at very long wavelengths. Okay, maybe give me another 5 minutes to actually, maybe, those of you numerical modelers, appreciate what we do in these, to compute these fancy-looking evolving landforms. As an example of one, okay? All the images I'm going to show you are not blown up. That is, this is actually, there's about 1,000 by 1,000 pixels in this image. It's a JPEG, 1,000 by 1,000. And I computed it, and each pixel is a numerical point at which I solve the equations. There's no interpolation between my numerical grid and the image. So you see the resolution we can actually reach, and I'll show you we can reach much more than that resolution you see there. Just I can't show it on the screen, there's not enough pixels. So these things are called surface processes models or landscape evolution models. There are many equations that comes into it, but the big one, it's the one that determines the rate at which I erode in the channels. And in fact here, I'm assuming that that law applies everywhere. It's what we call a detachment limited landscape, which happens in very highly tectonically active areas. There are other processes I won't talk about much today, but I could. The big problem, as you can see, is the problem of scaling. Why? Because the slope, in theory, the slope that matters here, in this real landscape that you really want to model, is the slope that you measure in the field. We're talking here, it's very common to go out in a mountain and have a slope at 60 degrees. Okay? A slope at 60 degrees, if you put a point every kilometer, you'll need enormous topography to have a slope at 60 degrees. So to sample properly these, you can show actually that the slope that matters has to be measured at a 10-meter resolution maximum. So your model should have a resolution of 10 meters, but you want to apply it to the Alps or a mountain belt, hundreds of kilometers. So you see the scaling problem that we have. So in the last 10, 15 years or so, I've been also working really hard to scale the M, the N, and the K so that we don't have to solve at 10 meters, but only at, a kilometer by all sorts of methods, homogenization methods, simple smoothing method that cannot be justified. So this is what we've been doing in the past. Why is it so difficult to do at high resolution? Because you have to calculate two things, A and S. Okay? A is, this is a zoom, as you've seen, my beautiful zoom of that area here. It doesn't show very well when I zoom it up like this. So each of these points, I calculate the solution, little pixels here, okay? At every point of this, what I have to calculate is the drainage area. So I have to compute which of the other pixels drains there. Okay, so if I drop water here, it'll go there. If I drop a drop of water, it will not go there. But I have to do that for all the points. And I'm not going to do it. There's only 2 points here. On the landscape. So you see the enormous computational requirement. It's an n-square problem. Okay, it's not, I've worked hard. I got it down in the last 10 years to n log n. And I'm going to show you. I got it down to n now. So, n being the number of points on which I have to compute it. And the other big problem is that S is in fact dz/dx. So this is a nasty nonlinear advection problem. Okay, and we all know numerical modelers. You know, we're going to have waves propagating through this. We want to keep them waves. You don't want to get some, all the numerical diffusion problem going to play here. So for that, we need extremely small time steps when we solve this, of the order of a year. And again, we have to solve this over tens of millions of years. So you see the problem, okay? So, I swear, this is in the last month and a half, I've actually went back to the drawing board because dynamic topography says, look, we need the technology to evolve. And so I actually devised, and the current process of publishing this is very, very new, a way to solve these equations very efficiently. And I'm going to very briefly show it to you. It doesn't depend on the discretization. It can be rectangular, it can be any. What you do is every point of the landscape where you want to solve the solution, the first thing you do is you connect them between them. You can use a regular mesh, or I do, in some cases, I use a Delaunay triangulation, or whatever. So you connect your points. That's one first thing. And then what you have to do, for every point, calculate the steepest link. Okay? So see, that guy was connected to many neighbors, conceptually, and that one defines the steepest slope of all its neighbors. So conceptually, if I drop a glass of water here, it will go down here. Okay? And that guy, so this is called the steepest descent, or the steepest slope algorithm, which is used in all of these models. Okay? And that will define the river network. The clever thing here is to really do this. Okay, I have that information. I know each node gives to one neighbor. And I can invert that. You can do that in n operations. For each node, the list of the neighbors that are giving water to me. Okay? It's a classic inversion in creation of what we call a stack. Okay? So I know at every point that this guy, I'm only receiving water from this guy. This guy receives from this and from that. So what I do, I start from the nodes that are on the boundary of the landscape, and these nodes are usually at sea level, and they don't move. It's what we call base level. So from those nodes, and there's a whole series of them, I go upstream and simply number the nodes, and every time I get to an intersection, I make a random choice. I go left here, okay? And then I go up, and then at some point, there's no neighbor above me, so I come back to the previous intersection, and I go in the other direction. And I come back, and I go there. Oh, you have an intersection there, you see? And I build this list from 1 here to 12. If you do that, you can also invert that list. That's trivial. You just take it on its head, and you have now a list from 1 to 12. And what's really cool with that list is that when I go from number 1, I take the water that rains on that point, and I give it to my lowest neighbor. In that order. So now I go to 2. Take the water that rains there and give it to my neighbor. Do the same thing here, do the same thing here. I can show that at any intersection, when I leave that intersection, I will have contributed, by definition of that list, all the contributing nodes that are upstream of myself. So when I get at that point, at every point here, I've calculated perfectly the drainage area, or the water, the discharge of the water at that point, in a number n of equations, the number of points in that catchment or in the landscape. Then it goes further, because we really want this to be efficient. You go back to the normal ordering, so from 1 to 12, and now that you know the drainage area, you can measure the slope, it's just the difference in height between the 2 points, I can solve that equation. And I'll show you why I solved that equation, now that I know that and that, in that order. And it's very important. I'll come back. I'll tell you why. And then, see, I'll do that, then I do it there, etc., etc. I reverse the order again. And I do the same thing as I did with the water, but now I do it with how much erosion I've predicted here. And by doing that, I accumulate down the network the sediment flux. How much I've actually eroded from the landscape and given to the river. Okay? So I have that another component of this that's very important, how much sediment is being routed at every point of the network. Again, I only need n. All these operations are order n, not n log n, they're only n. Finally, why do I need to compute the erosion in the normal order, that's where it gets really exciting. And this is something I'll be frank, an idea that came during discussion with Sean Willett, another geomorphologist in Zurich. And why would you want to do that? Because I told you, because of the nature of this, okay, when I update the height of this, I also change the slope. It's a problem with the advection problem, okay? So I need very small time steps. And typically, when you calculate the height here, you say it's it's just expressing this in finite difference way, okay? It's first year applied mathematics. The new height here is the old height there, minus the finite difference expression of that term here. I've put n equals 1, okay? And that's the difference in height between these 2 points divided by the distance between the 2 points. It gives me the slope, okay? Now, this typically is something you can do explicitly, because in theory, you don't know what you're trying, when you put on here, you use the estimates of the height here and here at the previous time step. That's called, you all know that, an explicit formulation. In fact, if you start from here, that point is fixed. Okay, that point doesn't move, it's at base level. So if I solve this equation here and here, I know that. I know that at all times. So I can use t plus delta t rather than t. Okay? And because z1 doesn't change, it's always the same, I only have one unknown here. It's z2 at t plus delta t. And you can actually, z2 at t plus delta t, because z1 is known. And you have here fully implicit formulation and solution of that equation. And you all know that if you have an implicit formulation, it's always stable, and it's accurate for much larger value of delta t. This means that I don't have to use 1 year or 100 years. I can use 1,000 years time step, and it's extremely stable. And I can propagate that up the system, because now I know 2. It only depends on 1, and 1 is fixed. If I go in the right order to calculate 3, I only need to know 2. And 2, I know it at the previous time step, at the next time step. So I can propagate this implicit formulation up the network and remain implicit at all steps, at all nodes of the network. That's what it says here. Better than that, you can actually show that whatever you do in one drainage area is, by definition of a drainage basin, is completely independent of what you do in the next one. So this is perfectly parallelizable. And if you use what the most recent technology in computers is called the core shared memory technology, you can think of, you put your landscape in memory, and all the processes, all the core of your laptop here, or your computer, are going to work on different parts of the landscape independently. And they don't really have to worry about the fact that one other guy is working here while I'm working there. All you have to do is at the end of the time step, you have to synchronize everything. So what you in fact do, for each of these rivers that end up here, there's many more than that, of course, you just give the work that this guy has to do up in that catchment here and that catchment there to different cores of your machine. And it's perfectly parallelizable. An example, just to show you, this is a 1,000 by 1,000. And this was, the computations you see here was done on my laptop here. That would have taken about 20 seconds to run on this machine. 1,000 by 1,000. That's 1,000,000 points, which you have to do this computation. And you do it for 1,000 time steps. So you see the propagation of the erosion wave. And then what I do halfway through the model, I increase the uplift rate. Okay, so the problem here is I have an uplifting zone at a given rate, doesn't change, and I'm eroding it away. Okay, and then halfway through the model, I increase the uplift rate by a factor 2. I'll play it again, and what you can see is, of course, the system is kicked by this uplift. Erosion propagates as a wave. It's very well known, this kind of behavior. And then as the second uplift phase comes in, we have a second phase of erosion. And what's interesting, at this point, now it's 1,000,000 years in the computation, I could uplift it, it will not change. So these geomorphic systems organize themselves in very complex ways, such that at every point, if you multiply slope to a power by drainage area to another power, you are exactly matching the imposed uplift rate. Okay, so everywhere on this landscape, if you make the product of slope by drainage area, you get a constant. And you can show that all these geomorphic systems will always evolve to that situation. So you can have what we call steady-state landscapes. In the real world, they will be perturbed by variations in lithology or in precipitation. But on the broad scale, we know that they exist. And they are very stable. These are not going to change much in shape. Maybe locally a little bit, but not very much. That's more boring. That's discharge. And it shows this is the water flux in rivers, you see. And at the beginning, what you see is that there's a lot of rivers are trying to find the location. And at some point, the incision is such that they're blocked. And then, see, that's it. No, they won't move. The drainage system is organized. Even when the second wave of uplift comes, they are fixed. Valleys and rivers are extremely stable in the landscape. And that's very well known too. A way to perturb that is to actually advect it horizontally. If you have a fault, okay, not only you uplift, but you move horizontally to the blocks. So they could do it. But here, we assume a vertical move. And finally, to show you how you reach the steady state, this is erosion rate. And I'll show you that it tends towards a constant, where the erosion rate must match the uplift rate, and you're at steady state. And, you know, it all becomes white. It's all at the same erosion rate. So everywhere, depending on the slopes are different everywhere, the drainage area is different everywhere, the system organizes so that the product of the two to some power is the same everywhere. Beautiful. The books, entire books written on the evolution of these systems. This is the evolution of the system in cross-section. So you see you reach first, this is the steady state, and then the second wave comes, and you're going to reach another steady state. Here we go. This is the mean elevation, the minimum, and the maximum elevation. And I can show you this. You see also, geomorphologists know that. These are called midpoints. Okay, this is how a river propagates that way. So the information that this point is at sea level, it doesn't change, while the rest moves, propagates always upstreams. Okay, so you see how you establish a profile for the river, and then as the second wave of uplift comes in, you have like a wave of topography that propagates. It's what geologists or geomorphologists call midpoints. It's waterfalls. Okay, when you walk down a river and suddenly it means that that river was perturbed maybe 1 million years ago downslope, and the step that has created is slowly migrating up the river, and you saw it propagating. Finally, last slide. Compute time normalized by something as a function of number of points in the grid. Perfectly linear. All the algorithms I'm using are order n. To the point that I had access to a machine that has 16 gigabytes of memory. This only has 8, okay? And I run it. It's got a fairly fast 8-core machine. This is solving 100 million points. So you solve these equations over 100 million points in about 2 seconds per time step. So we're talking really, when I run this on my computer in the train, okay, I always scare everyone because when you have the 8 cores running at that, it's really well scaled. Basically, the computer starts to cry and it goes shh, and the people around me say, "Oh, he's going to lose his computer here." This is really efficient use of the core technology. And it makes these computation extremely efficient. And this is, again, 1 over computation time is a function of the number of processors. And those of you who are in this field, this is a very nice scalability. The slight drop here is because this is done on my laptop. These are not, the way this works is there are actually 2 CPUs, each with 4 cores, okay, or 2 cores doing multi-threading. And so when you go from one CPU to the next, the bus is really a little bit in trouble and can really cope with the scalability. My conclusion comes from 2 papers in 2010, and this is published in 2010 as well. These are review papers or white papers about geomorphology, general field of geomorphology. Big challenge is a computing challenge. Basically, to come from that scale, this is the simulation of what happens in the southern half of New Zealand, where a simulation, this is about 80 kilometers. And this is a simulation done recently by one of my PhD students using another type of model looking at hill slope evolution, where you need a grid of 8 meters. And so what I'm suggesting now is that with this technology that I showed you, and that kind of scaling, that kind of times, we can get down to, we can, just make the ratio. If this is in tens of meters, that's 100 kilometers at a resolution of 10 meters. So we can easily now model this at that scale and extrapolate it to that scale. And I believe with the new technology that's coming out now, where we have machines that have up to 160 cores and 1 terabyte of memory for a reasonable amount of money, I'm talking about a few tens of thousands of euros, we could do this on our desktop without any problem. So, see, that's obviously something that excites me very much now. And I'm going to put a lot of effort to further develop these methods by adding all sorts of processes on, small-scale processes on the hill slopes, but also develop a much more subtle and correct river dynamics with braiding of the rivers, which is already done by others, but at the scale of a kilometer by 100 meters, you see. So now we can extrapolate this and have the proper coupling between that and that. And it's not just for the beauty of the numerics. Terraces that form in rivers that are used by geomorphologists all the time to do all sorts of things, they don't really know how they form. They form by getting stuff from the hill slope into a dynamically active river like this that's going to be choked with sediments, we cannot transport them, and then ultimately will transport them. So the physics of that link is critical to understand these features. And I'm already quite over time. This is just a repeat of what I said. Dynamic topography, our best bet to actually constrain it is from geological observations. That's repeating it. Eroding dynamic topography is, I believe, very efficient. And then we can use our normal tools to constrain it, like thermochronology, sediment accumulation. And I think we're not close. We have developed we're on the way to develop a truly predictive landscape evolution model, where we won't have to do homogenization or scale the parameters in some, very unknown way between the processes happening at human scale and the processes and their integration over scales, tectonic scales, mountain size scale. That's it. That's where I should go. Thank you.